I think it's starting. All right, so then I can go back to share screen. And I believe it's currently recording. And then I can go to screen show from the beginning. But okay, and then go forward. Okay, so there's two cases for the non-unity feedback. I'm getting echo now. Okay. Maybe I should turn mine down.
No, I think it was somebody else's mic.
Oh, okay. And then it's outside my control. All right, that's good, actually. Okay, so there's two cases that we would, different cases that we can, that can come up that we can attack. And the first one we talked about last time requires that the main idea is we have this adjustable block in the front, and by using one of the block diagram rules, I think it's number 4, we're able to move that connection or move that block past that summing point, so it's inside. And we find if we follow the rules, we have to put a 1 over, I guess, K1 here. And of course, because it's adjustable, we can always make the K1 equal to K2, and then the product is unity, and then therefore we're back to the scenario we had in the start of the whole discussion of this type analysis. So we made a comment which turns out to be useful in the example we did, and also I think there's a homework problem. That we didn't have to be so constrained that the feedback transfer function absolutely had to be a constant. In fact, we could allow it to be a S dependence. The only thing is we would want the be able to identify the limit for that transfer function for S going to 0 being some constant. In which case, because that's kind of like our steady state analysis, we know was based on the final value theorem where S does go to 0, and this is sort of what's behind all this. So we're saying, well, if we're interested only in the steady state analysis, error steady state, then in fact, this modification, or to replace the sensor H of S with the constant is okay, because our end result is strictly that we're interested in strictly the steady state error. And then we did that. We argue there's the block diagram rule, and then we applied that in this situation, saw that in the end, it just came down to the equivalent of moving the K1 inside, and the feedback path became a unity feedback. Then we had this example, and in the example itself, the H of S did have S dependence, did depend on S, but as you can see, letting S go to 0 just gave us the constant K2. So we used that idea, and we came up with we followed our rules. In this case, it was the GCG didn't have a pole at S equal to 0, so it was a type N equal to 0 system. And I believe for the input in this case was a step input, in fact, a unit step input, A equal to 1. And that's exactly the right condition for a finite error, not 0, but finite. And then, of course, that's because 1 minus 1 is 0. And we plugged in our position constant based on that new model for the system, and then we came up with that answer. So, any questions on that? That was what we did. I know we got that far last time.
If we Why are we looking? Why are we starting with something that's not a unity feedback if we end up having manipulating it to be a unity feedback?
Well, that's a good question, and the answer to that is, I think the answer that hopefully helps is that we don't know. I mean, the line of reasoning that we're using here is, you know, the problem you're given initially would not be a unity feedback. So you need to, the idea is, well, by converting it to the unity feedback, you can use all that machinery before, but how do you know what it is until you go through these steps?
Okay.
You know, it's sort of like saying, well, we moved the goalpost a little farther down the line, but we see how to fix it up so that we can still play the same game.
Okay. Yeah.
Okay. Did I answer your question or not?
Yeah, I got it. It just makes it,
It
I
just
guess,
adds
easier to work with.
It just basically, well, because we're saying, well, maybe there's situations where the actual system you want to analyze is not a unity feedback. And
Right, but we already
yeah.
had a process with the unity feedback, so we
And we
might as
already
well
had a
make it look like
process.
that.
That's right. So if we can jury rig it so it looks like what we had, then we can use all that machinery. That's right. I think that you got that right or not?
Yep.
Okay. All right. So then there's second method, which I thought we had started talking about, but I'm not sure we got very far. But yeah, I think we got through the page, but might as well review it real quick. The second method does not have some important differences than the first method. And number one would be that we do not have an adjustable block on the front end. So we're not going to be doing we're not going to pull that block transformation business. And actually our goal here is not to try to convert it to a unity gain system. It's really, you could argue, we could analyze this one for the restricted case that we're going to apply without all that type analysis. So the idea is we kind of go back to ground zero. We redefine the tracking error just the way it would have been consistent with before, however. We go ahead and plug in for the transfer function using the output is the transfer function times the input. And then we apply the final value theorem, and we're told that we're only going to be successful with this method for only one input type, and that's the type of a step input. And so we'll kind of see why it's so obvious it works is because, well, you get that for the step input, you get that 1 over s that's part of it, but then that s in the denominator for the step nicely cancels the factor of s that seems to be built into the final value theorem rule. So you get that immediate cancellation, and after taking s equal to 0, you get this recipe which completely sidesteps the issue of type analysis, but it does give us the steady state error. Any questions on that? And down here is supposedly an example of a system that, let's say, that would be applicable to. So I don't hear an example. I think we'll jump in on the I don't hear a question. We'll jump in on the example. All right. So here is the example for the second method. It is based on, I don't know how to get this thing to move. Anyway, it is based on this. It's based on the diagram at the top, where we see that yes, it's non-unity feedback, and the various so-called controller block, the so-called plant, or what he calls process, and then here's the transfer function for the feedback path. And in this example, we're following the main idea of the example. We're leaving the K that's in the controller as adjustable. Bear in mind, this is not the same as before because this block is on the inside. We're going to say, well, find that K to minimize the absolute value of steady state error. Okay. And that's, I believe that's the wording of the problem. And since we don't have an adjustable block on the front, what we're going to do here is we're going to apply this idea from the previous page. And also we're told that we're only interested in the unit step input, and that would mean A equal to 1. So our steady state error, then a special case of our steady state error formula that we had before, we set A equal to 1 because it's unit step, okay, the A being 1. And then all we really have to do is to come up with a transfer function for this closed loop transfer function for the system. And then after that, set S equal to 0. Okay, and then we're pretty much most of the way along to finish the problem. All right, so I trust that since we've had this practically come up from the very start of the class, the so-called canonical form recipe for transfer functions, you could see the GC and the G. Here, this is the GC. It would be the G, and there's the H. So that would, I believe, the correct canonical form recipe. The plus there is because the minus there, just to remind you. And then we plug in, and really, you know, we're going to set it equal to 0, but no sense, it really doesn't have to be so. It could be simplified if you wanted to, but it doesn't have to be. We can just straight away set the S's to 0. And when we do that, we see we get a K over 2 in the numerator, a K over 2 in the one factor in the denominator on the right, and a 2 over 4 one factor in the denominator on the right. Okay. Now, for purposes of where we need to go, for simplification, you could say only, we can multiply by 1, which is in this case 4 over 4. So we can, in fact, let me see here. Yeah. So, yeah. Okay. So we get 4 over 4, right? So we multiply through. Now notice that after we set the S equal to 0, this 2 and that 2 will cancel. So I'm not too worried about those 2s. They're going to go away automatically. So I do have that 1 over 4 there. So that 4 cancel this 4 and put a 4 in the denominator, and I'll get it. Basically, 4 over 2 is 2 and get a 2K there. So our expression, our general expression for the error prior to actually picking a K to minimize the error, we would say would be the following, just by plugging in that transfer function evaluated S equal to 0 right in where, according to the recipe, it needs to go. Now, as far as minimization here goes, the idea would be, well, we can see, well, I think we can see that if in fact we can make what's in the parentheses equal to 0, we would be doing as well as we could hope to do. That's the best scenario, is to get 0 steady state error. So, and it looks like that's possible because the K is selectable. So if we would set, and I could ask the question, but I think you're going to see it. What could we set the 2K over 4 plus K2 to get 0? Equal to
1.
1, right? So set it equal to 1. Then it just becomes an algebra problem for fault solving for K. And as you can see, that's the first step. Noticing you could take the K to the other side will lead you to the K equal to 4, and that would be the result. That would be the answer. Okay, I'm waiting for a question if there is one. Not hearing a question on that. Okay, I'm gonna go to the next page here. Okay, the next, this starts a second topic in chapter 5. A topic called dominant pole analysis. Now, almost was tempted to leave this off and go directly to root locus. However, I had forgotten that actually in the reading of root locus in there along the way, you're going to find some reference to dominant pole analysis. So I thought, okay, it's only a couple pages, we'll get it in. So at least when you read it and when you do the root locus, you'll know what it means. And so let's do that. So the concept behind the dominant pole analysis is really not that difficult. It's a pretty simple idea. And that is that, let's say, you solve the problem and, the results were pretty much a stable solution with decaying exponentials. And you hypothetically in this scenario, you had some linear combination of solutions, one with which went as e to the minus 3t, leaving off the u of t part, and e to the minus 15t, again leaving off the u of t part. And we know if we actually went to the computer and sketch these out, we would know that the one with the minus 15 as the coefficient in the exponent for the exponential would decay much faster than the one with the minus 3t. And one would argue that when comparing these two pieces of, let's say, a general solution, you'd argue that, well, the one with one of these would represent the dominant pole. Which one do you think it is?
E to the minus 3.
Yeah, because that's the one that lasts, right? In other words, it lasts longer. So the dominant pole is going to turn out to be the one that's is in fact going to have the longest longevity, whatever, in time, And however, it's not simply a greater than kind of thing. There is a rule which greater than something factor, so we'll see that. So it would have been considered an okay approximation, presumably, as long as you're not restricting yourself to too close to the starting point. It would generally considered an okay approximation to delete terms associated with certain poles or factors. Let's say we'll see. We'll see that all this business translates into what is happening in terms of the factors of the transfer function. Because we know if we have a transfer function, we can do a partial fractions expansion, and so they do correspond to individual terms. But sometimes when you give them the transfer function in that form, they're just simply multiplicative, as we'll see. All right. Consistent with the sentiment of the community, removal of a pole or poles is an okay approximation. Now, depending on what criteria you use, and I've seen cases where people have used criteria as high as 10, but I'm going to go with and as low as 5. We're going to go with 5, in the sense that 5 will be how fast does it have to decay to be neglectable compared to, let's say, the dominant pole. So we'll see a rule that will pop up here. So. And we would argue, it gives the summary, long-term transient response will not be significantly affected by the pole removal on the conditions we're considering. Now, the S going to 0 is kind of like, well, we know we know that time and S domains are kind of duals of each other in terms of reversals of how they what they correspond to. So low time, usually, we know the final value theorem, to do that one for t going to infinity, would correspond to, in the S domain, S going to 0. Okay. Now, what is the goal here? Well, the goal is, believe it or not, just no more, no less complicated than just having a simplified transfer function to work with. One that maybe you can quickly recognize as being a second order system, for which all the standard properties that, let's say, you're more familiar with would apply. Now, I don't think you're going to find this figure in the book. I believe I borrowed it from another text, but it kind of, I mean, I didn't see one like it in our book. And I kind of thought it represented pictorially kind of where we're going with this idea. So in the sense that what he calls it dominant poles, but we're going to compare simply to the most dominant pole. That we would have a region of poles which we wouldn't, could be as few as one, but we'll have, let's say, the so-called dominant poles. And if you went far enough to the left on the axis, real axis, and that would be our criteria. Whether the poles are complex or real doesn't matter, but the point is, if the real parts are far enough to the left, we're going to say, well, it's going to decay fast enough that we can ignore those compared to the dominant poles. So I really did like this picture, so I borrowed it from another book. Okay, so our first example here, hopefully is that, okay. I'm going to turn is that green bar interfering? Is there anything interfering with your view?
No green bar.
No green bar. Okay, that's good. Then I can go to my page, my hard copy here, which I always believe in hard copies if you can get them. My hard copy here, and then I won't have a problem. For some reason, I can't move that darn green bar, even though I want to. All right, I'm going back. Okay, whoops. All right, there. All right, so here is our hypothetical first problem. And we see that, as indicated, you know, we could argue that there's various terms in here. And we can simplify this expression using this dominant pole analysis. And we recognize that there's poles at s equal to 0, -2, and -30. Speak up if that's not clear. Now, from what you've seen already, you can maybe guess of these three poles, which one do you think is more likely to be neglected?
-30.
-30, right. So we can argue that that for sure that -30 pole would be, excuse me, would be in fact neglectable. Now the thing is, just to make sure you don't fall into the trap, we normally go through a little bit of an argument where we can just take a look at that s plus 30 down here. Notice if you rewrote it that way, that would be consistent with it, and that if you let s go to 0, you get 30. Now, I'm arguing, well, maybe we didn't need all that. Maybe all we needed to do, and if you see it that way, was set s equal to 0. But what you don't want to do, which will get you the wrong answer, you don't want to throw that whole piece away. That 30 is an important part of the information. So what we're saying here is, in order to get this approximate result, okay, keeping what are called the dominant poles here, the approximate result, you would argue, if you recognize which one you can throw away, and you could say, well, if we did compare it with the one at a -2, and you can see it, let's go back again here. You would say, well, that 5 times a -2 is a -10, but that's certainly more positive than a -30. Therefore, the one with the -30 can be thrown away. And therefore, you could say, okay, looking at the picture here, we'd say, well, we can approximate the one with the s plus 30, just throw a 30 in there, and then so that becomes k over 30 over s plus 2. So the pole with the -30 is removed. And here's the final result. It's approximate, but it's consistent with the dominant pole theory. Any question on that? Okay, now I'm going to go to the second example. Now in the second example, we have a quadratic, and the idea being, well, that quadratic in fact can in fact have complex roots, but our guideline can be and should be based on the real part of those roots. All right, so we can see that the first factor would have a pole at a -10 on the real axis. And if you did your quadratic formula arithmetic on this one, and I'll let you check me and tell me if you don't agree, I believe it should turn out that the roots will be a -1 plus or minus j. I'll let you check me on that. And therefore, since and the focus would then be not in this discussion, the imaginary parts of the roots aren't what count. It's the real part of the roots that we're doing our comparison with. So since the real part of the root is a -1, we can come back and look at our expression again. So which of the poles here looks like you can throw it away? The pole at
-10.
Yeah, -10. And again, let me remind you, the temptation, which would get you the wrong answer, would be to simply throw that whole thing away, but that 10 carries important information. So the correct way, the easy way to do it, not the way I show you necessarily here, the easy way to do it, just set s equal to 0, works fine. Now, if you want to factor it first and then set s equal to 0, that's up to you. But if you, either way, you do end up in that factor of 10 will survive. Okay, now notice that 20 divided by 10 is 2, and that's what happened. Now, could you have gotten there just by setting s equal to 0 here? Yes, of course. And I would say that's as good, or because it might be, or even better, because it might be one step faster. So if we then, you know, we can always do a quick check. If we take the limit that the s goes to 0, notice that here, back here, you would have gotten, let's see, 20 divided by 10, which is 2. 2 divided by 2 is 1. Yes, you get, you know, in the end, your result should be consistent with the original one, taking the limit s going to 0, at least as long as it stays finite. Any questions on that example? So our final answer would be, in fact, this one right here. That's our approximation after dominant pole analysis. All right. Unless there's a question, I'm going to go to the next page. Okay, on the next page, I think we got a multiple pole removal and an example with complex roots. All right. All right, with this multiple pole removal, we see, in fact, we have a 0 and a -3. And even though I can't see it on my screen, I got my hard copy here. We got a pole at a -1, -2, -6, and -7. All right. Now, I think to bear in mind in this analysis, what you want, you could say, well, you know, if you go back to the original figure that we had, you would say, well, somehow both the s+1 and the s+2 define the poles that would fall into the so-called dominant pole region. But really, for our test purposes, what we want to do is compare the roots, all the roots, to what might be called the most dominant pole. So now if we take a look here, what is the most dominant pole in this bunch? S equal to?
-1.
-1, right. So that's the most dominant pole. And because in fact we see that the one at a, there's also poles at a -6 and -7. -6 and -7 are more negative than a -1 by, let's say they're less than, like more, right way to put it, more negative than a -1 by a factor of greater than 5, right? Because, you know, 5 times the -1 is a -5, but these are more negative than a -5. Therefore, both both roots, not just one, but both roots are candidates for removal. And again, I say the shortcut, once you recognize that, the shortcut trick would be to set the s's equal to 0 in those factors that correspond to those neglectable root, poles. You can't just completely throw the factor away, because the information of the 6 and the 7 is important. So set the S is equal to 0 on those two, not the others, but those. And so 6 times 7 is 42. And then the K went along for the ride. There you go. And so this is the end result here from the dominant pole analysis is what we see. So what's the takeaway here? The takeaway is when you're doing this comparison, it's okay, go after the most dominant, you can and should go after the most dominant pole for pole removal purposes, because if we applied it with the S equal to -2, neither of these other two poles would qualify, and we don't really what we want to say is what is one of these poles is going to determine which other ones can be neglected. And certainly the correctly pointed out, the -1 is the dominant pole. Okay. Now that's why I could not throw the 1 and a -2 away. It's still part of the expression. Any questions? Okay, so far, in this last example for this topic, so far, all of our dominant poles have been strictly real. Unless I'm mistaken. No, that's not the case. Back here we had, yeah, okay. So this was dominant pole back here. All right. So, but here we got a little bit different. Now everything is all factored for us. So the question is, you know, let's just go through the evaluation here. So it's all factored for us, which makes it easy. You get, basically, you're going to get a pole at a -1, -2j, -1 plus 2j, a -10, and then here's a -50, -200j, and a -50 plus 200j. So we've got a bunch of poles in the denominator. And the argument would be that we can identify the ones that we can throw away. Okay. Now, based on our guideline, can you see which ones can be possibly thrown away?
Everything except the -1 plus or minus 2j.
Yeah, that's right. So you see, we got the one at -10. That looks pretty, it's going to end up being pretty negative compared to the -1 poles on the real axis, and also the -50. So we can see what's going to be thrown away. And you can argue, yeah, if you just go through and I guess you can cut to the chase on this. We follow our fast and sweet method of just setting S equal to 0. I think you can see what's going to happen. But let's take a look at now. Bear in mind, we need to keep the 10, important information, and we're going to need to keep this part right here. Okay. Now the reason I say that is because in this case we're throwing away parts that have complex conjugate poles. And yeah, we need to keep the important information associated with that, the 50 and the 200 there. So if we take a look at our we'll just do them one at a time. If we take a look at our D of S, there it is right there, where the part that we want to keep, notice the S's were not set to 0. And then the other terms, where the S's were set to 0, just setting S to 0 across the top. So repeating the first two factors, which we're going to keep just the way they are for simplicity purposes. There's the 10, because S 10 plus 0 is 10. And then here we get the part that's kind of a twist on, I think, on anything we've done before. We're just going to go ahead and take a look at that and simplify that, which we can do. And notice that these numbers are complex conjugates, and therefore, basically, A plus JB times A minus JB is just going to be A squared plus B squared. So a plus jb times a minus jb. So we're going to get the a squared plus the b squared. I'll let you check the arithmetic with your calculator, unless you can do it in your head. And therefore, we plugged that in. We got that extra factor of 10 that was built in up there. So now our near to final expression for the denominator that we need is right there. We'll put it in. And notice we can multiply the 10 times the 42,000 number, and there we are. Okay, so it's 425,000. And there we are. Any questions on that? Okay, I already posted the solutions for these this chapter 5C under homework 6C, and those solutions have been posted.
Dr. Pieper,
Yeah.
Did you start recording this session?
I believe we did. Anybody out there want to say you can confirm that?
Yeah, it's being recorded.
Okay.
Okay,
There's
thank you.
there's a formula sheet there at the end. I think that's the last page on that business. Okay, so let me escape and get out of here, figuratively. All right. So okay, so everybody see that page? Okay, that's from chapter 7. Hello?
Yes.
Okay. Just a quick comment. You know, if you look at the chapters in the book, most of them, with some exceptions, and this being one, most of them are sort of a potpourri of different topics just brought together. Other chapters are really pretty much devoted to one topic, and this is certainly one of them. This whole chapter is devoted to one topic known as root locus method. It may give you some idea of the significance of this topic in the field of controls. And I'm not going to dwell on that too much, but it's considered a pretty pretty standard important topic for control theory. Okay, so that's why we're going to jump in, better sooner than later. And so we're going to start, well, what is root locus? Well, root locus is a plot of roots in the S-plane as some parameter k changes. Okay, that gives locus of the roots. A collection of points that define how the roots change. Now, what roots, we'll clarify that later, but pretty much they correspond to the characteristic equation. Now, this is where, you know, you could say, well, what's the big deal about this? We all know, or we may have heard, if we don't not very familiar with, that there are algorithms for finding roots, you know, Newton's methods and at least 3 or 4 other ones. So in a way, that was my first impression. What's the big deal? You know, you just turn a computer and, you know, and even MATLAB will produce the roots for you. However, what we're learning here is an interesting collection of rules that essentially take the place of all that numerical analysis. And I'm not sure we would have it today if in you read down here, the original development for root locus goes all the way back to late 1940s, where some graduate student named Walter R. Evans thought he was going to find a fast way to avoid the pain and suffering that goes with the numerical solutions by doing what we have in this chapter. So he's one pretty much today is giving credit. So here we have a graduate student who's pretty much developed a new idea just to solve the problem that he had. And he just, I guess, he felt the numerical computation was getting too much of a headache for him. So I don't think he had MATLAB back then. But fortunately, maybe he didn't, because we now have root locus today. And basically, it's a collection of rules which tells us what's going to happen to the roots as we change some parameter k. So it does turn out to be a big deal. Now, some of the things you can do with these rules, I mean, I'm not saying you couldn't do them with the numerical methods, but again, one of the advantages of having this root locus would be you can check things like stability. Certainly, if you're describing a second order system, you can come up with the percent overshoot, the damping frequency, settling time, all sorts of things that go with second order. And hopefully, as we'll see, there's also a place for what is called proportional integral derivative type controller design. That's getting ahead of ourselves, but just to sort of give flavor where we could go with it. So that being said, let's go to the next page here. All right, we're going to start off pretty much. I want to be as much as possible be consistent with the thread of logic as given in the book. Okay, so we'll start with the initial test case or test block diagram, as you see it here, which has pretty much unity feedback. And I don't think I remember the book making a big deal out of this, but I think it's important for you to know that we're not really constrained in this method by having that we have to have unity feedback. But I think to start the discussion, that's why the author chose not to include the possibility of the non-unity feedback. But I'm going to mention it at least along the way, so you can bear in mind. There won't be any surprises later when it pops in, the effects of non-unity feedback. So, but however, we can see from the canonical form recipe that this would be the correct canonical form recipe for getting the transfer function. And all I'm going to do is, if I had a transfer function in the feedback loop, it would appear as we see it in the denominator, just so you know. So getting back, so in general, we would say our transfer functions ultimately will end up as a ratio of polynomials in the numerator and the denominator, and pretty much consistent with our same notation we use when we're doing the Roth criteria. Our characteristic polynomial Q of S, therefore, would be this factor right here. Now, I just take out just a second just to mention, of course, if you had a non-unity feedback, the H of S would appear right there where you'd expect it to be for that characteristic polynomial. Okay, so let's go ahead with this. All right, so if we set that characteristic polynomial to 0, we know that those lead to the roots, which define things like the stability criteria and where the poles are at for that consideration, the location of the poles. So it's a pretty important information. The K here is you may remember in the discussion, it is, well, how the poles move around as the sum parameter K changes. And for the purpose of this discussion, that parameter is the K that's in that block diagram. Any questions so far? Okay. Pretty much a fair number of the rules that we're going to need, at least several of them, are heavily based on two direct observations that you can make from this formula right here. The first one would be a simple matter of algebraic rearrangement, okay, which allows you then to say, and from that, okay, you can say the absolute value, okay, of the left side must then be equal to 1. That turns out to be useful for often for finding the value for k when you know where the poles are at. And secondly, another important rule that finds its way into the collection of rules needed for root locus is that the angle or the phase associated with that in general, I guess it would be, in general, it could be complex, but the point is we say k times g of s, okay, then would be 180 because it has to be equal 180 because at -1, right? If you say, well, if you look at the complex plane, if you go around you get a -1 when the angle is equal to 180. And to keep it as general as possible, we'll say, well, it didn't have to be 180. You could also add another 360 degrees and you come back around again, and you're still back on the, you could say on the negative real axis. So that you can have as long as k is an integer. Okay, any questions? I realize we just sort of started the subject here. Now, there's a point you might be good to make in this discussion. You notice that the two diagrams the diagram we had initially on the previous page, at the bottom of page 2, and the one at the top of page 3 are in fact different. And you have to argue the transfer functions are going to be different also. However, for purposes of root locus, the guideline that controls where the poles are and how they move with respect to that k parameter, we see is exactly the same with that we would have had with this diagram, right? Because if you go back with this diagram, the denominator is 1 plus k g of s. And with this, the canonical form with this one was also 1 plus k g of s. So there is no big secret here. It turns out that the root locus plots are not unique to the transfer functions. So it turns out because, let's face it, transfer functions have a numerator and have a denominator. And that just means you can have the same denominators and different numerators, and yet because it's the denominator part of the transfer function that dictates the root locus. In brief, that means that there can be situations where different transfer functions would in fact have the same root locus. And unless I'm mistaken, and I believe I've read this somewhere, the MATLAB people have elected to use a system model that's more or less based on the one at the top here. Now, bear in mind, it doesn't make any difference because as we see, the root locus is based on that 1 plus kg of s. And it's the same for both block diagrams. And even though they're different and they have different transfer functions, they have the same q of s, and therefore they have the same root locus rules. Any question on that before I move on? Because that issue kind of comes up again a little later. We'll see that that's and being open to that idea will be helpful later for another kind of problem that does come up in root locus. All right, so we're going to go back. We're going to go back to the original one, which we have here, and we're going to take a specific example and start talking about that one which is intended to get the ball rolling and get you some idea what it's about. So let's take as a specific example call it the plant or the process block 1 over s plus 2. Okay, so that's it right there. Okay, and we got the k, our root locus parameter k in the feed forward path. And so the example is pretty much explore the prediction of root locus, the locus of poles for the T of S using observations. And what we're going to do is we're not actually going to be using the rules. What we're going to do is we're going to go back to first principles and sort of point out along the way what some of those rules are to sort of get some confidence that, oh yeah, that you could have come to the same conclusion just by making that observation, kind of thing. So this is kind of going back to first principles approach. Here's our G of S. Oh, here is a point that you may want to make a note on or just kind of remember in case a question would come up. For our treatment in the book and in our notes, we're going to limit our root locus for the cases that the root locus parameter is strictly non-negative. So k could be 0, but it can't be negative. Okay. Now, you may say, well, is it impossible to find root locus treatments where k is negative? And the answer is no, you can find them. Usually treated as a kind of an add-on for clarification if you needed to use that, but for our purposes, we don't need it for problem solving. And if you're interested, I think there's maybe some discussion in the book on that, but it's usually considered like an add-on if you need it, if you need it. We're not going to consider that. So just remember that for everything we're doing regarding root locus, our root locus parameter is non-negative. Okay, real and non-negative. Okay, so if we go back to our transfer function here, you would agree this is it, and a little bit of simplification, all which many of you are already familiar how to do, or all of you, by essentially multiplying through by the SS plus 2 gets you to that form. And we see that then our characteristic equation, which is dictated by the denominator here, which determines the poles, set that equal to 0. That gives us our characteristic equation. Any questions? All right, so we're off and running on this business. So we see that, yes, the location of if we solve then this to 0, that tells us where those roots are, which are the poles of the right-hand side. Then we can use the quadratic formula, as you can see, negative b plus or minus b squared minus 4ac over 2a. And then a little bit of simplification gives us what we see here. All right. Any questions? Okay, so we'll start where, I'm not sure you would guess this, we'll start with the lowest possible k we can have, which would be k equal to 0. And we see that if we plug in k equals 0, we get the r plus and the r minus. The r plus would be, notice that would be the higher of the two would be at 0. And the negative one would be -1, -1, which would be a -2. So we're going to have, those aren't really arrows. They'll represent an X at the bottom. You can see that's an X there for a pole and an X there for a pole. And that would correspond to k equal to 0. How are we doing on time?
It's 10.
10 o'clock.
Is it 10 now?
Yes, sir.
Okay,
Yes.
so I should finish now. Okay, I'll follow the rules. I would ask you, maybe you want to read ahead if you have time. I will post some problems on this pretty soon. I just didn't have a chance this morning. And again, I'll remind you, I've already posted the solutions for under homework 6C. I posted those solutions. All right. Well, then we'll pick this up on Friday. And if you have a chance, start reading that whole first section there, covering this example. All right. Let's get out of this. Let's see how to do it.
I have a question.
Yeah.
Okay, I will wait a signal question.
What is what?
I will wait a signal time. The
Hi.
question is based on signal system.
Oh, okay. Okay. We're not worried about the signal. We're worried about the system in the sense that all we're looking at is the transfer function here. So this is all about the system having the so-called stability, non-stability type properties. So there is no discussion on input signal here. This is only the only focus is on the system itself.
Yeah, I understand.
Okay, so you won't see us injecting any RFS in there. I think that's what you're asking. It's a good question, but we're not going to be going down that path. Hopefully that answers your question, if I understood it correctly. Any other questions? All right. Then let's see. First thing, escape. All right, escape figuratively. Okay. And where's my? It's not doing it. How do I get out of this again? Stop share. Okay. All right. Okay. I'm ending the meeting now. All right. We'll pick it up again for 4311 in about an hour, I suppose.